Hi, a lot of students were asking me about this question, so in this video, I'll be solving it. It's a question from Stewart's calculus. Find the area bounded by y equals cosine x, y equals 1 minus cosine x equals 0, and x equals pi. Now, this is the original question in the book. Online, it may appear with additional factors like an 8 times cosine x here and then 8 minus 8 cosine x here, or some other number. Well, with or without the extra factor, it's solved the same way. So I'm just going to solve the question without the extra factors. All right, in computing area, you should always draw the graphs. Unless you know in your head what it looks like, you really should always draw the graph. This is true of finding the area under the curve or finding area between two curves. Let me do a quick sidebar on area under the curve before I go back to area between two curves. Let's say the question is to find the area under the curve of y equals fx for x from A to x equals B. Your gut reaction is, I'm just going to do the integral from A to B of fx dx. That's your first reaction, instinctive answer. But that doesn't always work. That's only correct if your function f has a graph that is completely on one side of the x-axis. A here and B here, then this integral is that area. If it's completely under the x-axis, and then you get a negative area, and a lot of us are fine with that because we're talking about the area under the curve. So if the curve is under the x-axis, then it's negative under whatever. That's fine. The problem is if the graph crosses the x-axis somewhere in here, like this A here and B here, then if you take this integral, then what happens is you have this negative area and you have this positive area. They will cancel. So when you take the integral from A to B of fx dx, you have the negative part canceling out the positive part, and this value is only equal to this leftover part. And that's not the question at all. The question wanted the area of the whole thing. The question didn't want you to cancel anything out. So how would you do this correctly? To do this correctly, you have to go this area separately, and that would be from A to some number here that you would have to find out of this negative area, negative fx. And then you add this separate area separately, plus the integral from x naught to b of fx dx. That way you get a positive area plus another positive area, and that will give you the area of the whole thing. Even in finding area under the curve, you have to pay attention to whether or not the curve and the x-axis cross each other. So now if we generalize it to the area between two curves, then you have to pay attention to when the two curves cross each other. Let's now talk about area between two curves. Just like area under the curve, things are really nice if one curve is completely on one side of the other without crossing. So if I have fx here and have g of x here, and I want the area between f and g from A to B, then all I need is area from A to B of the difference between them. Well, I still need to know if I'm going to do fx minus gx, I'm going to do gx minus fx. In this case, it'll be fx minus g of x. So this is the larger minus the smaller. In order to get the area between two curves, I always must do the subtraction between the larger minus the smaller, so I can have a positive number, right? And now you start to see what the problem is. The problem is if they start crossing each other, then what counts as larger changes. Let's say that f(x) looks like this, and g of x looks like this. A is here, and b is here. Then if I do integral from a to b of f(x) minus g of x, then f(x) minus g of x would be upside down over here, and it'll be negative, and f(x) minus g of x would be positive here. And so, for example, this part here is negative. It'll cancel out that part here that's positive. And if I do the integral from a to b of f(x) minus g of x, I only get this part. So integral from a to b of f(x) minus g of x, the x only gets me that part. It does not get me the whole area. How do I do it then? I have to find out where this intersection is, and I go integral from a to x naught of. Now, to the left of x naught, the larger function is g of x, larger minus smaller. And then I have to add on the second part, where now the larger function is f and the smaller function is g. And then add. Okay, so bottom line is, for area between two curves, I must first sketch the graph of the functions. Find all the points where they cross. They could be crossing multiple times between A and B. And then you compute separate integrals for each interval. In which each of the integral is integral from some intersection, something to something of the larger minus the smaller. Where which one is larger and which one is smaller may change depending on the interval. This is when we're integrating with respect to x, because we're looking at the difference from the larger here to the smaller there on a thin slice where the width of it is a small change in x, a dx. There are situations where the graphs are this way, and you may want to do it with a thin slice horizontally instead, where the thickness of it is a small little dy. So in this case, you take an integral, again, larger minus smaller, but larger now means the function to the right minus the smaller function to the left. And again, you're going to have to draw the graph so you can tell, am I better off doing this integral with respect to x or doing this integral with respect to y? And I got to catch all the intersections. For example, if this problem asks for the integral between c and d like that, then I have to do one integral for this piece, a second integral for this piece in between, and a third integral for this piece here on top. Same idea, just turn around on the y-axis. Now let's go back to our problem. All right, so we're back here. Let me write the steps on the side so we can follow them. Step 1 is to sketch the graphs. Step 2 is to find the intersections, if any. And step 3 is the calculus part, that is, do the separate integrals. do separate integrals between all the intersections, and then add. All right, so let's do step one. I need to graph cosine x and then 1 minus cosine x. The cosine curve looks like the sine curve, except that it starts at 0, 1. So it looks something like this. The complete cycle or complete period is from 0 to 2 pi. Our question stops at pi, so we're stopping here at pi. So that's our cosine x. Now, how about 1 minus cosine x? Well, we're going to use the methods of graph transformation from intermediate algebra or college algebra or algebra 2 or pre-calc that you previously took. This is cosine x. Minus cosine x is the opposite of that, so it goes something like this. So this is minus cosine x. And it's at -1. Well, 1 minus cosine x means negative cosine x plus 1. That means I'm going to shift it up by 1 because the y value goes up by 1. So I'm going to shift this up by 1. And I end up with this curve. So that's 1 minus cosine x. And it goes all the way up to 2. Those are my two curves, and I see ahead of time that I will have to have separate integrals. Have to have one integral between 0 and this point right here, x naught that I don't know yet, where this integral is cosine x minus the 1 minus cosine x, the solid graph minus the dashed graph. And then from x naught to pi, the second part, where the larger function is the dashed line, you have to be the dashed minus solid. So I know ahead of time that I will need integral from 0 to x naught of solid minus dashed, and a separate one from x naught to pi of dashed minus solid. And then I'll be adding them together. That means I need to find out where that intersection x naught is. And that's why we have that step 2. Well, we find the intersection by setting the two functions equal. Add cosine x both sides. And divide both sides by 2. Cosine x equals 1/2. What does that make x? Well, in my head, I tend to visualize the unit circle, where 1/2 is here on the cosine axis, and that gives me this angle, which is a 60-degree angle, because all of these special numbers is either 30, 45, or 60. And that's pi over 3. There's also a mnemonic device using fingers on your hand, and I had a separate video about that, so check it out above. Either way you do it, I got x equals pi over 3, which is my x naught over here. Right, so I'll be doing an integral from 0 to pi over 3 of cosine minus the other function, plus integral from pi over 3 to pi of the other function minus cosine. In the first part, from 0 to pi over 3, it is cosine minus the 1 minus cosine. And then from pi over 3 to pi is the other way around, is 1 minus cosine x minus the cosine x. The first integrand simplifies to 2 cosine x minus 1. And the second integrand simplifies to 1 minus 2 cosine x. Integral of cosine is sine. Integral of 1 is x. And I plug everything in. Sine of pi over 3 is square root 3 over 2. All of this is the value at pi over 3. Now I plug in value at 0. Sine of 0, 0. When x equals 0, then the second term is also 0. That's a big 0. Plus, now I plug in the value of pi. Sine of pi is 0. And sine of pi over 3 is square root 3 over 2. I put them all together. This minus and minus makes a plus. So I have a total of 2 times the square root of 3. And now I'm looking at all the pi's. I have negative 2 pi over 3, because there are 2 of them here and here, and plus a pi. And 1 pi minus 2/3 pi is 1/3 pi. There it is. Once again, let's summarize the process. To do area between two curves, you must do, number 1, sketch the graph. Number 2, find all the intersections. And number 3, do separate integrals for each interval, where within each interval, the integral is of the larger function minus the smaller function. If it's dx, then it means the top function minus the bottom function. If it's dy, then it means the right function minus the left function. Right? Hope that helps. Any questions or comments, write in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.